When we think about super advanced technology, our minds usually jump to stuff that's bigger, faster, flashier. But in Japan, some of the most amazing innovations aren't about spectacle at all. They're actually about survival. Today, we're going to dive into how Japan's greatest challenges, like its super volatile geology and its incredibly limited space, have literally become the blueprints for its most essential, life-sustaining engineering.
And this quote, it's really the key to understanding everything we're about to talk about. See, in a country that's constantly dealing with earthquakes, typhoons, and floods, technology isn't some luxury item. It's a fundamental necessity. The big question isn't just, hey, what cool thing can we build? It's what's going to happen if we don't act. And that philosophy, well, it completely changes engineering from a show of power into an absolutely essential tool for resilience.
All right, let's start with the most famous constraint of all, earthquakes. For decades, there was this real confidence in Japan's structural engineering, but then the Great Hanshin earthquake hit in 1995, and it just shattered that belief. It was a brutal wake-up call that completely changed the country's whole approach. It forced engineers to think way beyond just withstanding a quake, and toward designing buildings that people could actually live through, completely unharmed.
And that brings us to this beast, the Nakanoshima Festival Tower. I mean, at first glance, okay, it's a 200-meter-tall office building. But the really mind-bending challenge is what's going on underneath it. It is sitting directly on top of a massive 2,700-seat concert hall, basically a huge open cavern with no columns inside for support. So how on earth do you build a skyscraper on what is essentially empty space and somehow make it one of the safest buildings in the world?
Well, the first part of the answer is right here. It's called a giant truss, and it's basically this massive three-dimensional web of steel beams. Think about a simple bridge, right? How it's built with all those triangles for strength. This is the exact same idea, just on a colossal scale, and it's built inside the building. Its whole job is to gather up the entire weight of all the upper floors and sort of funnel it around the open concert hall, directing all that load down into 16 gigantic prime columns on the edges.
And the scale of this is it's staggering. That internal megatruss system is holding up 38,000 metric tons, the entire skyscraper, and rerouting all of it through that complex steel skeleton. But here's the thing, while that gives it incredible strength, strength alone isn't enough to survive a major earthquake. The real magic is in how the building also moves.
And this is where the real genius comes in, mid-story seismic isolation. What the engineers did was essentially install a flexible layer of massive shock absorbers right in the middle of the building. I want you to picture putting the entire office tower on a set of really sophisticated roller skates. This allows the whole top half to just glide and sway gently, moving totally independently from the violent shaking of the ground and the concert hall down below. So here you can really see the cause and effect. On the left, that's a lead rubber bearing, one of those giant roller skates. It's a stack of rubber and steel plates with a lead core that can literally deform and just soak up energy. And on the right, that graph shows you exactly what it does. The crazy, chaotic shaking that enters the building at the bottom gets smoothed out in a huge way above that isolation layer. It actually cuts the violent acceleration felt on the upper floors by about 75%. Just amazing. But innovation isn't always about inventing something totally brand new. Sometimes, the most brilliant ideas come from rediscovering the incredible wisdom of the past. Take the Tokyo Skytree, for instance. Its secret for surviving earthquakes doesn't come from some modern computer model. It comes from centuries-old traditional architecture. And this just illustrates that connection so perfectly. For centuries, these 5-story pagodas in Japan have survived countless earthquakes. And the secret is that central pillar, the shimbashida. Now, it doesn't actually hold the floors up. Instead, it's a massive freestanding counterweight. So when the outer frame of the pagoda sways one way, that heavy core sways the other way, canceling out the vibrations. Well, the Skytree uses the exact same principle. Its huge concrete core acts like a balancing pole for a giant.
Okay, so let's shift gears now. We're moving from the challenge of an unstable Earth to the challenge of, just not having enough of it. Japan's cities are so densely populated that they face an extreme scarcity of land, so when you can't build out, you have to get creative, and that means you have to build down.
You could seriously walk past an entrance like this every single day and never ever think twice about it. It just looks like any other garage door, but what you're actually looking at is the gateway to an automated parking system, a high-tech solution to the space problem hidden like a secret base right under your feet.
And then you see what's hidden inside. It's this vast, multi-story labyrinth of steel. It's like a high-tech beehive built for cars, operating just beneath the city's surface. This isn't just a garage. It's a massive, automated, three-dimensional puzzle solver.
For the user, the whole process is just beautifully simple. You drive your car in, you get out, and you walk away. That's it. From there, this incredibly complex ballet of lifts and conveyors takes over. A central computer analyzes your car's size, finds the most efficient open slot, and shuffles vehicles around like a master chess player to park it, and then retrieve it for you just minutes later. It's a perfect example of using complex robotics to solve a very simple everyday problem. Where do I put my car?
So this whole philosophy, using intricate technology to manage huge constraints, it goes way beyond just passive structures. The next set of innovations we're going to look at aren't just designed to stand strong, they're designed to be first responders, actively working to protect human life when disaster finally strikes.
Yeah, the idea for modern rescue robots, it wasn't dreamed up in some futuristic lab. It was born in the rubble of that same 1995 earthquake. That event tragically showed just how dangerous search and rescue is for the human responders themselves. It's so important to understand that this tragedy created this undeniable, urgent need for machines that could go where people couldn't. And that led directly to robots like Quince.
And these machines are just incredible tools. They are purpose-built for the absolute chaos of a disaster zone. They use crawler belts to climb over piles of rubble. Some can even slither through tiny gaps just like a snake. And they're packed with thermal cameras to detect body heat, which helps them find survivors who might be totally hidden from view. But not all life-saving tech operates on the surface. Just like those parking garages, one of Japan's most monumental engineering marvels is completely hidden from sight. It's called the GCANS project, and it is the world's largest underground floodwater diversion facility, designed to protect Tokyo from catastrophic floods.
So when heavy rains from a typhoon threaten the city, floodwater gets diverted into this absolutely colossal system. People call it the underground cathedral because of its sheer scale and these massive support pillars. At its heart are 4 jet engine-powered pumps, powerful enough to discharge all that water into a safe river at a rate of 200 cubic meters per second. To put that in perspective, that's enough power to empty an entire Olympic-sized swimming pool in about 12 seconds. So whether it's a skyscraper that literally moves with the earth, a hidden garage that solves the puzzle of space, or a robot that goes into a disaster zone first, a really clear pattern starts to emerge, right? This is a totally different way of thinking about what technology is even for. And what this all really points to is a philosophy where the goal isn't to be flashy or to shout about how amazing your tech is. Instead, this kind of engineering prioritizes quiet resilience. It's all about creating systems that just work in the background to ensure stability, to allow the normal rhythm of daily life to continue, totally uninterrupted by a crisis.
Ultimately, this whole thing is a story of turning constraints into catalysts for innovation. Every single piece of technology we've looked at was born from a very real limitation and then shaped by a crisis. They aren't designed to simply impress us. They're designed to provide practical, life-sustaining solutions that help an entire society adapt, stay safe, and just keep moving forward. And all of this leaves us with a pretty fascinating question. It proves that sometimes the most powerful innovations don't come from having infinite resources, but from the simple necessity of navigating our toughest limitations. It really makes you wonder, what could we all create if we started viewing our own biggest challenges not as obstacles, but as the clearest possible blueprints for progress?